This is the integral we ultimately want to solve. Your first instinct might be to use substitution, or integration by parts, or even change of variables as seen in the previous video on the Jacobian. You can try any combination of these techniques and you will be able to do the innermost integral and possibly even another one, but not really the whole thing. So since all the standard techniques fail, does this mean that this integral is impossible? Not really, because there is a very clever trick. First, note that the integrand is the distance between 2 points and we integrate over the unit disk. If we add a factor of 1 over pi squared in front, then this whole expression is the average distance in a unit disk. If you want more details on how this corresponds to average distance, check out the first video in this series. But how do we actually compute this average distance? The first key insight is to generalize this to a disk of radius r, not just the unit disk. The answer to this depends on r, so let's call it some function f of r. However, this doesn't actually generalize things too much, because if you double the radius, the distance should also double on average. On the other hand, if you halve the radius, the average distance will be halved. In fact, we have f of r to be proportional to r. We ultimately want the average distance in a unit disk, so we want f of 1, which is just the proportionality constant k. But here is the second key insight. K is also the derivative of f, which means that we want to find this limit. Side note, if we insist on using the lingo in the previous video, the numerator is the distance of nearby points after f, and the denominator is the original distance between two nearby points. So this ratio really is the scaling factor of f near the point r. But moving on to computation, we will consider this expression only. You might be wondering, why not this much more common expression of derivative instead? Well, the reason will be clear later on. Anyway, this suggests that we need to find the relationship between f of r and f of r minus delta r. Let's consider a disk of radius r and another slightly smaller one of radius r minus delta r. Then we write the average distance on the larger disk by breaking down into cases. Case 1. The two random points lie in the inner disk. The average distance in this case is by definition f of r minus delta r. Case 2. One lies inside the inner disk, but the other is in the outer annulus. Let's call the average distance in this case as some function that depends on the two radii. Finally, case 3. Both points are in the outer annulus. Again, we don't know what the average distance this is, but let's say this is some other function that also depends on the two radii. Now what we want is an overall average, covering all the possible cases of the 2 points. This means that all these averages would still be useful, but we need to weigh them according to how likely each case will appear. Applying these weights and adding the products should give us f of r, the overall average distance in the larger disk. By the way, this weighted average step is usually called the law of total expectation. We now just need to figure out the probability of each case happening. In the first case, 2 points are inside the inner disk. The probability of any point being inside is the proportion of the area of this inner disk, which is the square of the ratio of the radii. If we need both points to be inside, the probability will be this whole thing squared, and we get the ratio of the radii to the power 4. We can expand this, but for reasons that will become clear shortly, we will ignore terms of higher powers of delta r. Next up, we have the case where one is inside the inner disk and the other is in the outer annulus. The probability of any point being outside is simply 1 minus the probability inside, and so the probability in this case is the product of these two, and also the factor of 2 here, because this product simply calculates the probability of the first point inside and the second point outside, but we also have the second case. So we do need the factor of 2 here. Anyway, we expand this a little bit, and it turns out that there is only one term that we need to keep track. So we are left with 4 delta r divided by r plus some higher order terms, which we ignore as in the first case. The final case is where we have both points outside the inner disk. The probability in this case is the probability of one point outside squared, which we can again do some algebraic manipulation to expand, but in this case all the terms are of higher powers of delta r. So we ignore all the terms here and say that this probability is approximately 0. So we can fill in the table now. The first case has probability approximately equal to 1 minus 4 delta r over r, the second case having probability 4 delta r over r, and the final case is so unlikely that its probability is negligible. Finally, we apply the weights and add them up, and we get that the overall average f of r is this expression here at the top. But we wanted something slightly different, which can be obtained in just a few steps from now. First off, we move f of r minus delta r to the left side of the equation, then divide both sides by delta r to get this. Finally, we let delta r tend to 0. The left side, as we discussed in the beginning, goes to f prime of r. And for the right side, we pretty much just eliminate delta r from the terms due to continuity. Note that this is now an equal sign, because if we really add all the terms back, the terms that we ignored are all like these: some constant unrelated to delta r, some positive power of delta r which tends to 0 as delta r does, and a bounded function in delta r. So in the limit, all these will disappear and we are safe to ignore them. This is usually called Crofton's differential equation. Let's take a bit of a break and appreciate how incredibly powerful this is. First, we reduce the problem to finding g instead of f, which is usually much easier. Secondly, this whole derivation only relies on the law of total expectation and some simple algebraic manipulations, which is quite elegant. Finally, this can be generalized to way more general situations. In fact, this is the most general form of the differential equation. The nu at the bottom denotes the measure of the region, generalizing the notion of lengths, areas, and volumes, which in this case is simply the area of the region pi r squared. Mu refers to some sort of average quantity we are after. In this particular case, we want the average distance f of r, but it can be an average of a lot of quantities you want. Distance is just one of them. It can be distance squared if you want, and in general, it can be a quantity that depends on n different points, but this quantity is subject to some restrictions. It needs to be symmetric, so if I swap any pair of points, the quantity is still unchanged. Distance, for example, would be symmetric, because swapping 2 points doesn't change the distance between them. The second restriction is that the quantity is bounded. As long as the quantity we take the average of fulfills these two criteria, this differential equation would hold. N here denotes the number of points that the quantity depends on, so n equals to 2 in our case. Finally, we have mu1, which basically generalizes the idea of g, something that we will be tackling very shortly. But before that, I think it's important to note that this supposedly much more general differential equation can be derived using pretty much the exact same argument, and I highly encourage you to flesh out the details of the derivation, perhaps in the comments below. Anyway, let's finish this up by finding g. Let's recall how we defined g in the first place. It is the average distance when a point is inside the inner disk and the other is outside. When delta r becomes smaller and smaller, the inner disk expands, so the point supposedly outside has to move towards the circumference to stay outside. So in the limit, g of r refers to the average distance where one point is inside the disk and the other lies on the circumference. One last thing before we do any computation. By the rotational symmetry of the setup, we can always rotate so that the point on the circumference is on the horizontal axis. So now there is only one point free to move. We then set up a new coordinate system with the leftmost point as the origin, and now we are ready. The average distance is by definition this integral. Again, this definition has been established in the first video in the series. Anyway, U denotes the domain we want to take the average over, and in this case, it is the unit disk. So the measure of this region is pi r squared. But how do we tackle this integral over the unit disk? We specifically chose this coordinate system because the distance is actually distance from the origin. Normally, I would denote this to be little r, but there are enough r's in this video already, so let's call it rho instead to avoid confusion. And yes, we will be using polar coordinates to perform the integral, so that now the distance is simply rho. However, because we will be using polar coordinates, we will need to add the Jacobian determinant, so this is what we are going to integrate, but we don't know the limits yet. Recall that in the previous video, to evaluate a double integral, we can either integrate with respect to y first, then to x, in which case the inner, upper and lower limits would depend on x, because for each strip, the upper and lower limits are different. However, the outer limits are constants, referring to limits of what values x can take. And of course, we can also integrate with respect to x first, then y, and the limits are analogous to the previous case. It turns out that in this case, it is easier to integrate with respect to rho than theta. The upper and lower limits of theta is the easier part, because the points in the disk take angles that run from minus pi over 2 to plus pi over 2. The slightly more difficult part is determining the limits of rho given theta. Given an angle theta, the point has to lie on this line. It is easy to see that the lower limit is just 0, but the upper limit requires a bit of work. We simply use this triangle and note that these lengths are r, and then by slicing this isosceles triangle in half and a bit of trigonometry, we have two copies of our cosine theta, and so this is our upper limit of rho given theta. Going back to our integral, we substitute our limits and we can now proceed. However, what we just calculated is still just g of r, not the original f of r that we want. We would need to solve this differential equation, and you could do that using some standard techniques, but we have f of r equals k times r, where k is the ultimate answer we want. Now substitute these into the differential equation. So here we have it. The average distance in a unit disk is 128 over 45 pi. So the quadruple integral is 128 over 45 pi, but this is the version with the 1 over pi squared factor in front. So if we want the quadruple integral in the thumbnail, it would be 128 pi over 45. But wait, it doesn't end here. What we have just done is the average distance in the unit disk, but what about in a unit ball? If you know spherical polars, I highly encourage you to repeat the exact same argument in this video as an exercise and leave the details in the comments. The answer you should get is 36 over 35. What about the average distance in an n-dimensional ball? The general formula is quite complicated depending on whether n is odd or even, but all these can be computed using the same argument as we have seen. And if we plot these average distances, we can see that when n increases, the average distance increases, but in the limit, it goes to square root of 2. If you want more details, there is a link in the description, which is the paper that I based this video series on. Thank you to these patrons, and as always, like, share, subscribe with notifications on, and leave a comment. Bye bye.